Thank you very much, Jay, for the kind introduction. Hi, everyone. Today, I'll be talking about how cloud providers can enable a safer and more reliable confidential computing platform on their machines. This is a joint work with Alex Schultz, Byoungyoung Lee, and Pedro Fonseca. As we're all aware, cloud machines today process a significant amount of personal information through the myriad of services that rely on the cloud. Given the sensitive nature of this data, it is extremely important for us to protect it from potential attackers, like other tenants on the same machine as ours. Cloud providers are not oblivious to this requirement of privacy. In fact, many of them leverage Intel SGX today to achieve confidentiality. Just to give you a recap, SGX is a set of CPU extensions that allow us to create a protected execution environment called an enclave on the machine. Users can remotely verify that they're talking to an enclave and send the sensitive data only to the enclave. Once data is protected within the enclave, it cannot be accessed even if an attacker is able to compromise the privileged software on the machine, like the operating system. Despite the desirable security properties of SGX, however, it still lacks many features that are required by cloud providers today and users. For instance, it is very important for cloud providers to have control over their machine. They want to know who is using enclaves on the machine so that they can build them. They also don't want people to run malware inside enclaves. But if cloud providers want to have this level of detailed orchestration, they must rely today on the operating system. The same operating system that could be compromised by other tenants on the machine. From the user's perspective, enclaves have been vulnerable to many digital side channel attacks over the years. And these side channel attacks can be leveraged by an attacker that controls the operating system to steal sensitive information from enclaves. And despite the severity of these attacks, there is no protection against side channels provided by SGX today. One of the ways we could do is to wait for the hardware vendor to update the CPU and then to add the features that we need. But this is not really a desirable option for us today. And that is for two main reasons. The first being that CPU updates are complex, so they take a long period of time. For example, an update from SGX version 1 to SGX version 2 took Intel 5 years. They're also uncertain. We don't really know the features that we need will actually be implemented. For example, we've known about side channels for the last 20 years, but we still don't have CPU updates to address these problems. Instead of relying on the hardware vendor to address these problems, what if we had a privileged software layer that we could leverage to augment the features provided by SGX? This layer could, for instance, be the hypervisor, which is controlled by the cloud provider on machines today. If we could leverage the hypervisor, we could rapidly deploy custom extensions and custom features as we require, as the cloud provider or the user requires. The big problem, however, is that SGX is designed in mind not to trust any external software. So for us to be able to rely on the hypervisor requires us to narrow the threat model of SGX. The question we ask ourselves is it realistic if we narrow the threat model of SGX so that we can rely on the hypervisor for flexible extensions of features? We believe it is for our specific use cases. So the two use cases we care about, the first one is orchestration, which is a feature that the cloud provider needs. The cloud provider would have no problem in actually trusting the hypervisor because they control the hypervisor and to be able to implement orchestration features using the hypervisor. The other important service that we care about is providing side channel protection against a compromised operating system. So if we trust the cloud provider, we can know that the complementary protection against these attacks will be correctly implemented within the hypervisor. If our trust on the hypervisor is misplaced, for example, the hypervisor becomes compromised, well, in that case, the standard protections of SGX against a hypervisor still remain, which means that the hypervisor will not be able to directly access SGX enclave data, providing us fully complementary protection in case our trust is maintained. And this is precisely the reason why we leverage a hypervisor layer to augment the features provided by SGX in our work. Specifically, eOPF empowers the cloud provider to create protected services, which are essentially a sequence of steps that should be taken during the execution of an enclave. The framework will instrument the relevant events during the enclave's execution, like when an enclave starts executing or when the enclave stops, and instrument the protected service to enable a new feature like flexible side channel protection. To be able to instrument new features at the hypervisor level, for us to be able to instrument new features at the hypervisor level, there are two important requirements to fulfill. The first one, as I mentioned, is that we must be able to trap the relevant enclave events. Specifically, we should be able to trap all enclave events if we want to build a general enough framework. This means all events from when an enclave is created to when an enclave is deleted. However, SGX does not natively provide the ability to intercept all of these events at the hypervisor level, and critical events like when an enclave starts executing and when it stops are not supported for traps. The second major requirement is that the framework and the enclave should be on the same machine if instrumentation is to happen. Now, this might look like a simple and trivial requirement, but it's actually trickier to achieve than you might think. Specifically, a remote user would want to know two things. They want to know that they're talking to an enclave, and they want to know that the enclave that they're talking to is on their cloud provider's machine. And they want to leverage SGX's attestation protocol for this. However, SGX's attestation protocol only guarantees the first thing. It tells you you're talking to an enclave. It doesn't tell you about the location of the enclave. So co-location cannot be verified using SGX attestation alone. In our design of the framework, we address both of these challenges. To trap critical events, we leverage the idea that even though hypervisors cannot natively intercept SGX execution events, there are still several features that are enabled for general software introspection. Specifically, when an enclave is created, we leverage memory protection features to make the enclave memory region not executable. The result of that is that when the operating system tries to start an enclave and transition into the enclave region, it raises a trap, signaling an enclave entry event. During the execution of the enclave will stop to service interrupts and to handle system calls. The framework is able to trap interrupts using the interrupt interception feature already enabled at the hypervisor layer. And to trap the execution of system calls, we leverage a single-step debug trap, which allows us to trap at the first instruction outside an enclave, allowing complete interposition over all enclave events. To attest co-location, we leverage the idea that hypervisors know which enclaves are co-located on their machine, and they could mark them for SGX attestation. Specifically, the protocol follows such that the cloud provider initially installs a certificate on the machine, which a remote user can then use to establish a secure communication channel with the framework on some machine. Once this channel is established, the user will then negotiate a watermark with the framework. This would be a random and unguessable watermark that will be known only to the user and the framework. For every enclave that is created on the machine by a specific user, the framework will apply the watermark during creation into the memory region of the enclave. And finally, a user can then use SGX attestation to verify that the watermark exists inside their enclave, and if it does, they're able to attest collocation. And through a combination of these two design points, we built a framework that allows us to implement diverse new features for SGX enclaves. We built two specific features to solve the two problems that I initially talked about, which is the lack of secure orchestration and side channel defense. Specifically, one of the protected service we built is the secure orchestration service, which allows the cloud provider to implement a runtime monitor over the usage of enclaves and even prevent other enclaves from being created if a user is not trusted. And it also allows the feature to be able to scan the initial enclave code for malware signatures to prevent a user from loading malware into the enclave. The other service we built provides strong side channel defense against a range of attacks against the operating system. While I'm happy to discuss each of these features offline, in this talk, I'm only going to briefly discuss the side channel defense service. Just as a recap, the reason why side channels are a problem is that system resources are shared significantly during execution between the operating system and the enclave. The tried and tested method of preventing these side channels is to partition the system resources when an enclave starts and to clear the system resource when the enclave stops executing. And there are many CPU features that allow us to be able to perform this partitioning and clearing. But the enclaves can't use them because enclaves are unprivileged. So what the eOPF side channel service essentially does is ensures that whenever enclaves start and whenever enclave stops, these features are correctly programmed at these events to ensure isolation between system resources. And finally, eOPF can enable these two features that I talk about, side channel protection and secure enclave orchestration, while providing very high performance. We ran a sequence of real-world programs with both of these services enabled, and we observed that while there are some occasions where a very highly memory-intensive program will incur high performance overhead because of cache isolation and invalidation, for the vast majority of programs, we observed very low performance overhead with a geometric mean of only 17%. In this particular state, the system was transparently enabling strong side channel defense against a range of system resources, while incurring a very small runtime cost, showing the practicality of the framework. So what do I want you to take away from this talk? Well, the idea here is that enclaves are awesome, but if we can complement the services that SGX provides with a software framework, we can improve and strengthen the protections that we have today against an untrusted operating system, all the while making sure that we can build rapid custom extensions to the feature set provided by SGX. Thank you so much.